Mr. Antonucci here, and in this video, we're going to talk about everything you have to know for AP Calculus Unit 4, which deals with contextual applications of differentiation. First thing is interpreting the meaning of the derivative in context. The average rate of change of f over the interval c to x is given by delta y over delta x, which equals f of x minus f of c all over x minus c, as long as x is not equal to exactly c, where delta y is the change in y and delta x is the change in x. Now, the derivative f prime of c equals the limit of the average rate of change of f as x approaches c. That is, we have f prime of c equals the limit of the average rate of change. Now, the derivative of a function f at the number c is the slope of the tangent line for the graph of f at that point. Now, we have to remember that the derivative of a function is just the instantaneous rate of change at that point. Another important tip is the units for the derivative, if you think of it as dy dx, are just the units for y divided by the units for x. And this applies to the second derivative as well. It would be the units for the first derivative divided by the units for x. This is where we get feet per second squared for acceleration, because acceleration is the rate of change of velocity. Velocity is feet per second, then acceleration is going to be feet per second, or feet per second squared. That brings us to talking about straight line motion and making the connection between position, velocity, and acceleration. The function x of t is often used as the position function of the object at time t. That's typically going to be used with horizontal line motion. You may see y of t, and that would imply vertical line motion, or you may see s of t, which is just the position function for an object. Now, the velocity function v of t is the derivative of the position function x prime of t, or you might see that as dx dt equals v. The acceleration function a of t is the derivative of the velocity function, so v prime of t, and therefore it is the second derivative of the position function. Now, a couple important points. If the velocity and the acceleration have the same sign, then the particle is said to be speeding up. Now, if they have opposite signs, then the particle is said to be slowing down. And remember that speed is the absolute value of velocity. Velocity tells you how fast you're going and in which direction, whether it's forward, backward, upward, downward. Speed is just the magnitude of that. It's the absolute value. It's always going to be non-negative. Now, if the velocity of the particle is negative, then the object is moving to the left. If the velocity is positive, it's moving to the right. And if the velocity equals 0, the object's going to be at rest. Now, there are many other contexts in which the rate of change can occur. Some important points to note is that when a quantity is increasing, its derivative, or the rate of change, is going to be positive. Similarly, when a quantity is decreasing, its derivative, or its rate of change, is going to be negative. Also, if a question asks about the rate of change of a rate of change, that's basically the derivative of f prime. In other words, the rate of change of the rate of change is the derivative of the derivative. Then we moved on to solving related rate problems. We talked about 4 main steps. First, you want to identify your knowns and unknowns. Definitely going to write those down, sketch and label a diagram if that's appropriate. Also, second, write an equation that relates the quantities involved. Make sure you don't plug in any quantities that are changing until the end. Third, you want to differentiate both sides with respect to time t. That's going to be using implicit differentiation. You're typically going to multiply by dx dt or dy dt or dr dt. Then fourth, plug in the known values, solve for your unknown, and always, always, always be sure to include your units. Then we talked about approximating values of a function using local linearity and linearization. So this is the idea that you can use the tangent line to a function at a point to approximate the value of a function for nearby values. F of x is approximately equal to the linearization of x, which is equal to the tangent line equation, which is going to be f of c plus f prime of c times x minus c, where the point c comma f of c is where you're making the tangent line. And then tangent line approximations will be overestimates if the curve is concave down, and the tangent line approximations will be underestimates if the curve is concave up. In other words, if you have a graph that's curved upward, anywhere you put a tangent line, the tangent line is going to ride underneath that curve. So if you pick any point near the point of tangency, the tangent line is going to under approximate it. Conversely, if you're concave down and you pick any point on a concave down part of the graph and you make your tangent line, it's going to ride on top of the curve. And therefore, points near the point of tangency are going to over approximate the function. And finally, we talked about L'Hopital's rule for finding limits of indeterminate forms. Now, indeterminate forms are when the limit of a function approaches either 0 over 0 or infinity over infinity. L'Hopital's rule is kind of an if-then statement. If the limit as x approaches c of f over g equals 0 over 0 or infinity over infinity, then that's going to be equal to the limit as x approaches c of f prime of x over g prime of x. We didn't do the quotient rule here. This is the ratio of the rates of change of f and g. Now, you may need to use L'Hopital's rule more than once if that new limit is still indeterminate. There are, however, 5 other types of indeterminate forms. They are 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, as well as infinity to the 0 power. Now, these can typically be manipulated to be able to apply L'Hopital's rule by rewriting them somehow so that you get either 0 over 0 or infinity over infinity. All right, guys, that's everything you must know cold for AP Calculus Unit 4 in order to be successful. Hope that was helpful to you. If it was, make sure you like this video, drop me something in the comments, and make sure to subscribe to the channel for more AP Calc videos.